Kafka worker slash Docker file. Inside Docker file from golang colon 1.21 colon alpine as build. Next line work dir space slash off. Next line copy go.mod space go.sum space dot forward slash. Next line run space go mod download. Next line copy space dot dot. Next line run cgo underscore enabled equals 0. Next space goos equal linux space go build dash o kafka worker dot slash cmd slash main dot go. Next line from alpine colon 3.18. Next line copy dash dash from equal build slash app slash kafka worker slash usr slash local slash bin slash kafka worker. Next line entry point open square bracket quote forward slash usr forward slash local forward slash bin forward slash kafka worker closing square bracket. For kafka worker slash go dot mod, first line in go module space kafka worker. Next line go 1.21. Next line require open parenthesis. Next line github.com slash segment.io slash kafka dash go v0.4.29. Next line github.com slash redis slash go dash redis slash v9 v9.3.3. Next line github.com slash hdrhistogram slash hdrhistogram dash go v1.1.0. Next line github.com slash prometheus slash client underscore golang. Next line v1.14.0. Next line closing parenthesis. Kafka worker slash cmd slash main dot go. First line package main. Next line import open parenthesis. Next line code context. Next line encoding slash json. Next line code fmt. Next line code log. Next line code os. Next line code str conv. Next line time. Next line github.com slash segment.io slash kafka dash go. Next line github.com slash redis slash go dash redis slash v9. Next line github.com slash hdrhistogram slash hdrhistogram dash go. Next line github.com slash prometheus slash client underscore golang slash prometheus slash prom http. Next line net slash http. Next line github.com slash prometheus slash client underscore golang slash prometheus. Next line closing parenthesis. Next line var opening parenthesis. Next line lat histogram equal hdrhistogram dot new argument 1 comma 60 underscore 000 comma 3 closing parenthesis, which this line comment means track 1 ms to 60 seconds latency. Next line hist registry equal prometheus dot new registry open and close parenthesis. Next line p50 equal prometheus dot new gauge prometheus dot gauge ops open parenthesis. Next line name colon code worker underscore latency underscore p50 underscore ms comma help colon code p50 latency ms comma. Next line closing semi-curly bracket closing parenthesis. Next line p95 equal prometheus dot new gauge argument prometheus dot gauge ops opening semi-curly bracket. Next line name colon code worker underscore latency underscore p95 underscore ms comma health colon code p95 latency ms comma. Next line closing semi-curly bracket closing parenthesis. Next line p99 equal prometheus dot new gauge so etc. And then we have func init function with one line inside hist registry dot must register p50, p95 p99, closing semi-curly bracket, then type message struct, open semi-curly bracket, and next line id, string colon code JSON colon code id, next line user id string, etc. Then body ts, closing semi-curly bracket, and we have func main, etc. And then we have inside this func main we have go function for http.handle, and then we have another go function for range time.tick, and then we have Kafka worker, Kafka.new reader after this function, Kafka.reader config. Inside we have brokers colon string, closing, then defer.close, ctx equal context.background, redis CLI colon equal redis.new client, and redis.option addr colon redis addr, next line defer redis CLI.close, then next line 4 open semi-curly bracket m comma err colon equal r.fetch message argument ctf. So first, a React client that uses the browser web transport API to send or receive datagrams ready to run in a create React app environment. Second, a Go Quick server example. So this is basically explaining that code. A Go Quick server example datagram echo that shows how to receive or send quick datagram using quick.go, plus an explanation about the importance between a raw quick datagram server and a browser web transport server, so you know what to run in practice. Third, a Terraform skeleton that deploys the AWS pieces you asked for, Kinesis Stream, Lambda, Node.js, Consumer, DynamoDB table, IAM roles, or policies in an event source mapping, Kinesis to Lambda. The TF is minimal but usable. You can expand it for production, VPC, KMS, CI or CD, dead letter queues, retries, etc. I'll include instructions for running locally and notes about browser requirements, TLS/http/3/web transport support. If you want, I can also produce a CloudFormation version. So first, a React web transport client, send datagrams, requirements and notes, important. Web transport is an API available in Chromium-based browser behind HTTP/3 plus web transport capable server. The client code below will run in a secure context HTTPS and talk to a server that supports web transport over HTTP/3. If you want a quick way to test Cloudflare Workers plus Cloudflare's web transport support, or a server built with a web transport enabled HTTP/3 server, see notes after the code. A raw quick datagram server not speaking web transport/HTTP3 will not accept a browser web transport connection. This client sends small datagrams, less than 1 to 100 bytes recommended. Quick datagram frames are mapped to UDP packets which avoid fragmentation. Now we create a React app, Vite, CRA here, shown as minimal React plus Vite, save as src/app.jsx. First line, import React, open semi-curly bracket, useEffect, userep, useState, closing semi-curly bracket from code React, semicolon. Next line, export default function, app, open semi-curly bracket, next line const, opening square bracket status, use status, closing square bracket equal use state, code idle, semicolon, const transport ref equal use ref, argument null, const read ref equal use ref, argument null, semicolon. Const messages, set messages equal use state, open parenthesis with inside it an open and close square bracket, semicolon. Then these next codes will change to your web transport server origin. Must be HTTPS plus HTTP/3 plus web transport. Const server equal process.env.react underscore app underscore wt underscore url double vertical line code https colon slash slash localhost colon 8443 semicolon. Next line, async function connect open semicurly bracket. Next line, set status open parenthesis code connecting semicolon. Next line, try open semicurly bracket. Now, so for this try, inside it, the next lines will create web transport session. Const transport equal new web transport server plus code dot slash web transport semicolon, which means server path that accept. And the next line, transport ref dot current equal transport semicolon. Next line, await transport dot ready, which means receives one session established. Next line, set status argument connected semicolon. Next line, datagrams var writable const writer equal transport dot datagrams dot writable dot get writer. Next line, so this next line will start reader for incoming datagrams. Const reader equal transport dot datagrams dot readable dot get reader. Next line, read ref dot current equal reader, then async, then try while const if const, then catch console, and then this next lines of code is a small ping example, sends 10 datagrams. So for let I less equals to 0 semicolon I less than 10 I plus plus, then const await set message await new promise closing semicurly bracket, then next line await writer dot release lock. So it's an optional line of code. The next line will tell how to graceful close after 10 seconds. So set timeout async if try set state 1000. Next line, catch error console.error set state closing semicurly bracket, then use effect. Next line, return. So this inside return is a cleanup. If read ref that current that cancel that catch, then if transport that read current, then closing semicurly bracket, then return div with the style padding colon 20 font family colon sans serif. Next line, h2 web transport demo client. Next line, p status. Next line, button on click connect end send 10 datagrams button. Next line, div style margin top colon 20. Next line, h3 messages. Next line, div style max height colon 300 overflow colon auto comma border colon 1 px solid number add comma padding colon 8. Next line, message that map m comma I. Next line, div key equal I style equal padding colon 6 background colon m from equal client. The next time, small I. Next line, pre style. Next line, div. So closing semicurly bracket. Next line, div. Next line, div. Next line, div. Next line, closing parenthesis semicolon. Next line, closing semicurly bracket. How to run React? First, create React app, Vite or CRA, and paste above into app.jsx. Second, npm install /npm run deb or npm start. Third, set React underscore app underscore wt underscore url equal https colon / your dash server colon 8443 in .env or change the URL inline. Fourth, open browser. Chrome 106 plus support web transport experiments. Stable builds include it behind flags or in recent releases. Ensure your browser supports web transport. Second, go quick server datagram echo quick-go. What this server does, it uses github.com/lucas-clement/quick-go to run a quick server that accepts quick connection and reads or write quick datagrams. It echoes any datagram back to the peer. Important, this is a raw, quick datagram server. Browser Web Transport requires the web transport over HTTP/3 handshake, and HTTP/3 requires that upgrades to Web Transport. A raw, quick datagram server that does not implement the Web Transport/HTTP3 handshake will not accept browser Web Transport sessions. Use this server for experimenting with quick datagram frames using a custom quick client, non-browser. For true browser web transport, you must use a server implementing the Web Transport Protocol. See notes. So here is a server/main.co. It's a simple quick server that accepts connections and echoes quick datagrams, requires go.mode with quick-go in github.com/lucasclement. Now we start with the first line, package mint, next line import, open semi-curly bracket, next line context, next line crypto/tls, next line flag, next line fat, next line log, next line time, next time quick quote github.com/lucasclement closing parenthesis, next line var addr equal flag, that's string, var cert file, var key file, then func main function, and next line fog.parse tsconf comma err, then next if err log.fatal closing listen comma r equal quick.listen add addr comma tsconf quick config, next line enable datagrams true closing if err not equal to nil log.fatal listen comma %vcode comma err, next line log.printf listening quick on %datagrams enabled /n code comma code addr, then for if err const go function handle session log.print defer, then for if, then if func gentle, then in, so that's it. And then for go.mod file module quick -dgrab-server, next line go 1.21, next line require github.com/lucas-clement. How to run server: first install go, and then go mod tidy, second create TL cert and key, self-sign for deb. In bash, open /x509 -new key rsa:2048-nodes-keyout server.key-out server.pem-days365 /subj code/c equal us/sd equal deny/l equals springfield /0 equal acme/cn equal localhost. Third, go run main.go. Listen on 4443. Fourth, use a quick capable client, not browser web transport, to send datagrams, i.e. a small quick go client that calls send message/receive message. Important, browser web transport compatibility. Browser web transport require the web transport over HTTP/3 handshake, HTTP/3 request with colon protocol semantics. A raw quick server will not accept the browser's web transport handshake. Options to accept browser web transport: use a server library that implements web transport, Go or Node. There are emerging libraries, web transport-go at mar10-cman work, etc. They implement the web transport handshake and then allow datagram frames. Use a reverse proxy/web server with web transport support, CATI with plugins or Cloudflare. Workers or Cloudflare can terminate HTTP/3 plus web transport and forward to your backend. Use Rust or C++ servers that support web transport, i.e. quick base web servers or dedicated web transport server implementations. If you want, I can provide a small Node server example using Node-HTTP3 or web transport/server. If you prefer Node, but note those server libs are not in core Node and may require native modules/build steps, or provide a Go web transport server example using a tested library. Tell me which language you prefer and I'll produce a runnable web transport over HTTP3 server that browsers can talk to. Third, Terraform skeleton. Kinesis / lambda / DynamoDB / IAM / event source mapping. This is a minimal Terraform configuration. It creates Kinesis stream, events stream, DynamoDB table, events table, IAM role and policy for Lambda to write into DynamoDB, Lambda function resource, zip uploaded from local path, event source mapping, Kinesis to Lambda, assumptions and prerequisites. You will build the Lambda zip node consumer locally and place it at /lambda/consumer.zip. The Lambda runtime here is node.js 18. Terraform remote state, modules, environment, production hardening are omitted for brevity. Replace AWS_region, account_ID and your email at example.com placeholder as needed. Providers.tf, so we just got that. Approaches for coping with load. Now that we have discussed the parameters for describing load and metrics for measuring performance, we can start discussing scalability in earnest. How do we maintain good performance even when our load parameters increase by some amount? An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load. If you are working on a fast-growing service, it is therefore likely that you will need to rethink your architecture in every order of magnitude load increase, or perhaps even more often than that. People often talk of the economy between scaling up, vertical scaling, moving to a more powerful machine, and scaling out, horizontal scaling, distributing load across multiple smaller machines. Distributing load across multiple machines is also known as a shared netting architecture. A system that can run on a single machine is often simpler, but high-end machines can become very expensive, so very intensive workloads often can avoid scaling out. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. Some systems are elastic, meaning that they can automatically add computing resources when they detect a load increase, whereas other systems are scaled manually. A human analysis the capacity and decides to add more machines to the system. An elastic system can be useful if load is highly unpredictable, but manually scaled systems are simpler and may have fewer operational surprises. See rebalancing partitions on page 209. While distributing stateless services across multiple machines is fairly straightforward, taking stateful data systems from a single node to a distributed setup can introduce a lot of additional complexity. For this reason, common wisdom until recently was to keep your database on a single node, scale up until scaling cost or high availability requirements force you to make it distributed. As the tools and abstraction for distributed systems get better, this common wisdom may change, at least for some kinds of applications. It is conceivable that distributed data systems will become the default in the future, even for use cases that don't handle large volumes of data or traffic. Over the course of the rest of this book, we will cover many kinds of distributed data systems and discuss how they fare not just in terms of scalability but also ease of use and maintainability. The architecture of systems that operate at large scale is usually highly specific to the application. There's no such thing as generic one-size-fits-all scalable architecture, informally known as magic scaling sauce. The problem may be the volume of reads, the volume of writes, the volume of data to store, the complexity of the data, the response time requirements, the access patterns, or usually some mixture of all of this plus many more issues. For example, a system that is designed to handle 100,000 requests per second, each 1 kilobytes in size, looks very different from a system that is designed for 3 requests per minute, each 2 gig in size, even though the two systems have the same data throughput. An architecture that scales well for a particular application is built around assumptions of which operations will be common and which will be rare, the load parameters. If those assumptions turn out to be wrong, the engineering effort for scaling is at best wasted and at worst counterproductive. In an early stage startup or unproven product, it's usually more important to be able to iterate quickly on product features than it is to scale some hypothetical future load. Even though they are specific to a particular application, scalable architecture are nevertheless usually built from general purpose building blocks arranged in familiar patterns. In this book, we discuss those building blocks and patterns.